The early 20th century was an amazing time for modern physics. One of the biggest discoveries was the quantum theory of light. We've discussed the photoelectric effect that really confirmed the photon theory of light. And this theory was further supported by an experiment done by Arthur H. Compton in 1923. Compton directed electromagnetic waves with very short wavelengths, what we know as X-rays, at stationary electrons. What he found was that the waves that were produced after the collision were slightly longer than the incident X-rays coming in before the collision. This is indicated with a lambda prime to distinguish it from the incident wavelength. Now we know that the frequency and wavelength of light can be described in terms of the speed of light. So if the wavelength after the collision is more than the wavelength before the collision, that must mean that the frequency after the collision is less than the frequency before the collision. So as our wavelength increases, the frequency decreases. Now we also know that the energy associated with light has to do with its frequency. So there is some amount of energy associated with the incident X-ray because of its frequency. The scattered X-ray will have a different, smaller energy associated with it because it has a lower frequency. So where does this energy go? Well, remember we had a collision with an electron. Compton simply applied the conservation of momentum and conservation of energy to the collision. So the electron that was sitting there minding its own business before being bombarded with X-rays was now in motion. So just like with a collision with a billiard ball, the collision of the photon in our X-ray sends the electron off in some other direction. We can describe this direction as some angle theta from the original direction of the X-ray. We can describe the angle of the scattered wavelength as well with the Greek letter phi. Let's look first at the conservation of momentum in this situation. To make this a bit easier, we can say that the incident ray is coming in towards the electron along the x-axis. This lets us say that the initial momentum is all contained in the x direction. So the incident X-ray coming in has some momentum that is equal to h over the wavelength. Now the scattered X-ray is moving off at some angle represented by phi. So the momentum of this X-ray will have an x component associated with it. We can represent this x component of the momentum of the scattered X-ray as h over lambda prime times the cosine of phi, with lambda prime representing the new, shorter wavelength. The now moving electron also has an x component to its momentum, and we can represent it as the momentum of the electron times the cosine of theta. So momentum in the x direction can be written as h over the wavelength of the original X-ray equal to h over the new wavelength, or lambda prime, times the cosine of phi, added to the resulting momentum of the electron times the sine of theta. Now momentum in the y direction starts out with 0 since we defined our incoming X-ray along the x-axis. After the collision, however, the scattered X-ray and the electron both have momentum in the y direction. For both, we can say that they both have momentum in the y direction that corresponds to the sine of their respective angles. So total momentum in the y direction is 0 equal to h over lambda prime times the sine of phi, subtracted from the momentum of the electron times the sine of theta. Note that we have to subtract because the momentum of the electron is moving in the opposite direction of the momentum of the scattered X-ray. So now let's look at the conservation of energy. The energy initially coming in is equal to h times the frequency, but we are a bit more interested in talking about this energy in terms of wavelength. So we can substitute in c over lambda for the frequency and show the energy as hc over lambda as the energy of the incoming X-ray. After the collision, we have the energy of the scattered X-ray as hc over lambda prime. Since the electron is now in motion, we can say that it has kinetic energy. And following the conservation of energy, the kinetic energy of the electron must be equal to the difference in energy between the incident X-ray and the scattered X-ray. So when the frequency of light decreased, it lost some energy. This energy was transferred to the electron, and since the electron is moving, that energy is considered kinetic energy. Of course, we can relate kinetic energy back to momentum. From ages ago, we know that the kinetic energy is equal to the momentum squared divided by 2 times the mass. So the energy conservation equation for the Compton effect can be written as hc over the incoming wavelength equal to hc over the scattered wavelength plus the momentum of the electron squared over 2 times the mass of the electron. So now we have three expressions that we can use to describe the Compton effect. At first glance, these expressions can be a little daunting, but look a little closer and we see that we know quite a few of those variables. We know the speed of light is 3 × 10⁸ meters per second. H is Planck's constant. We also know the incoming wavelength since it is an X-ray. We don't know the scattered wavelength, and we don't know the angle the scattered wavelength leaves, or the angle the electron leaves. And the last thing we don't know is the velocity the electron is traveling at, or the momentum, or the kinetic energy, whichever way we want to describe it. We are pretty interested, however, in the shift in wavelength, or delta lambda. Of course, delta anything is final minus initial, so our incoming X-ray is lambda prime minus the incoming wavelength. This is what is known as the Compton shift. Now there's a lot of math involved here that we really don't care about today, so we are going to wave our magic math wand and find that the change in wavelength is equal to h over the mass of the electron times c. All of that times 1 minus the cosine of phi. It might be a little surprising to find that the shift in wavelength depends on the angle the X-ray is deflected. But think about what that would mean if the angle is 0. That would mean that the X-ray has not been deflected, and the cosine of 0 is 1. So our equation would multiply everything by 0, which would mean that there is no shift. Zero shift, of course, would be the minimum shift that could possibly occur. Another situation could be that the X-ray bounces straight back from where it came, making the deflection angle 180 degrees. The cosine of 180 is -1, so delta y would be 2, and that would be the maximum shift that could possibly occur, which in our equation we would have 2h over the mass of the electron times c. That would be the most the wavelength of an incoming X-ray could possibly shift. Let's look at this ratio for a second. This ratio has a specific name. It is known as the Compton wavelength, and it is the wavelength of the electron as it moves away after the collision takes place. Notice also that this ratio is made up of constants. We can plug in all those and do the math, and find the Compton wavelength to be 2.43 times 10 to the -3 nanometers. So the Compton effect is the shift in wavelength that occurs when an X-ray collides with a stationary electron. This shift in wavelength helps support the quantum theory of light. The wave theory of light would predict that no change in wavelength would occur because the incoming electromagnetic wave would cause the electron to oscillate with the same frequency as the wave. If this were true, the oscillating electron would re-emit electromagnetic radiation in the same frequency. Since we do observe a change in the re-emitted wavelength, this suggests that the electromagnetic radiation is composed of photons that carry energy that depend on the frequency of oscillation of the photon.